Hello, everyone, and welcome to today's webinar, EV Modeling Capabilities of TAITherm. In this webinar, we will discuss how ThermoAnalytics is undergoing a major initiative to develop tools for electrification modeling, recent and ongoing xEV modeling efforts, and case studies that illustrate the most important modeling aspects of xEV design. My name is Chris Niva, Marketing Operations Coordinator at ThermoAnalytics and host of today's webinar. Our presenter today is Zach Edel. Zach is a senior research engineer who has been with ThermoAnalytics for over 5 years. Zach is TAI's resident battery expert and chief engineer of the TAITherm battery extension. He is involved in thermoelectric and thermal CFD simulation, advanced physics modeling, algorithm development, and multi-physics coupling. He has over 13 years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. In 2013, he received his PhD in mechanical engineering mechanics from Michigan Technological University. Throughout this presentation, you may submit questions in the questions box and we will review them at the end. We're also recording this webinar and we'll be sending you a link following this presentation. With that, Zach, if you're ready, you may begin. Zach, I think you're muted still.
Oh, I'm sorry about that. Okay. So today I'll be going through a few case studies and some discussion slides. The first two case studies are cabin comfort during cool down and warm up. The third is a battery thermal management. And then we have Joule heating, electric motor modeling, and system level modeling with 3D thermal integration. So a lot of people are talking about an electric vehicle tipping point when we'll see a lot more xEVs on the road. The xEVs stands for electric vehicles, hybrid electric vehicles such as mild hybrid or plug-in hybrid. So kind of the gamut of electrified vehicles, so not necessarily ones without an engine. And this group of vehicles is going to overtake sales of traditional internal combustion engines by 2030. And the PHEV and BEV sales will grow quick over the second half of this decade, and the battery sales will represent over 20% of the global market. And some of this will be affected by ride sharing, such as taxis and ride hailing services, where it's easier for people to share vehicles, and hybrids are already widely used in these areas for taxi business. And then the battery electric vehicle sales in the second half of the decade should rise to more than about 30% a year. And thermal management is becoming increasingly important in xEV design because there are different systems with interconnected functionality that all require cooling for lifetime purposes and performance. So we have HVAC, which is controlling the cabin comfort, both heating and cooling. We have the electric motor, power electronics, and the battery. And so these are interconnected because if the electric motor or the battery get too warm, you get derating. The power electronics are on the same cooling system as the electric motor, and sometimes those share cooling heat exchangers with the HVAC system and so on. And all of these systems influence energy budget and range. So in a conventional vehicle, particularly for heating the cabin, the heat comes from the internal combustion engine. In the battery vehicle, it all comes from the battery, as does the cooling systems. So since range is so critical, the energy management has a big effect on customer acceptance. So this is on the left here, you see a map of the energy usage per mile averaged over a fleet of Nissan Leafs in a year. And what you notice is we've got some high places in the south where air conditioning is required. In the north, though, is really where the energy usage comes in, and that's from heating the cabin. And The temperature also influences the battery performance. So at very low temperatures, the battery has very low capacity. And also you have to heat up the battery at low temperatures to get it to an operating point, which isn't going to damage the battery and which gives you the performance that you expect. The first case study I'll go through is a cool down cabin comfort scenario. And HVAC really affects the energy budget of your vehicle. The climate control load causes range reduction between 17 and 37% in summer and 17 and 54% in winter. And these are also affected by drive cycle, where you're driving, and the temperatures outside. So energy management is critical for meeting all of the customer expectations, especially when you're selling to customers around the world, the same model vehicles. And ThermoAnalytics offers several tools to meet these expectations. We have TAITherm, which is our flagship software, CoTherm, which is a co-simulation software that we offer to couple with TAITherm. And then we have a battery extension, an exhaust extension, drive cycle extension, and human thermal comfort extension. And we can also couple to other tools such as 3D CFD and 1D system tools, and those are generally coupled with our software via CoTherm. In this example, we have thermal CFD coupling, where TAITherm calculates the surface temperatures of all the surfaces in the vehicle. And then those are mapped into a CFD software. In this case, we're using OpenFOAM. And the CFD software predicts the convection coefficients and fluid temperatures at an element level. And these are mapped back and forth and coupled until they reach convergent state. And then they're run at different points during the drive cycle. And I believe drive cycle here is used to interpolate between them. For a cabin comfort, you typically don't have to run drive cycles. So I'm not sure if that was included in this simulation, but it's one of the benefits of thermal CFD coupling with TAITherm. And another consideration here that TAITherm's especially good at, particularly for cabin comfort, is solar loading and ambient weather conditions, so that you can get good initial conditions for your scenario, and then also look at how the sun is heating up the cabin and how much of it goes through the glass surfaces and so forth. So the AC cool down scenario has vehicle preconditioning, which is a hot soak in Phoenix, Arizona. The human is preconditioned by 2 hours transient in an office setting. So we're assuming that the car's been sitting all day in a parking lot, the person's in an office and then comes out and gets into the car. And that's important for the comfort prediction, because it takes into account the history of the people in some extent, and also gradients in like core temperature and limb temperature. This is a 30-minute AC cool down. The vehicle's at constant speed, 50 miles an hour, and it's max air conditioning. There's 4 vents in the dashboard and 2 in the rear console. And here we can see the near wall air temperatures at different times throughout the simulation, quite a bit higher at 1 minute, and then they decrease and they're pretty low at 30 minutes. But this isn't the critical thing we want to look at. The critical thing is actually the comfort of the passenger. So this shows HVAC, or the heat transfer coefficient boundary conditions. And here we have the surface temperatures. And this gives us an idea of how we're doing in terms of uniformity of airflow and effectiveness of maybe people in different parts of the cabin. And then this is what we're really interested in. This is the human thermal comfort and sensation results from this model. Sensation is on a scale from -4 to +4, where -4 is very cold, +4 is very hot, and then 0 is neutral. So optimally, you want to keep people around a neutral sensation, but when they change environments, it sometimes feels good to be in the opposite of where you just came from. So if you're outside and you're really hot, you want a cool sensation and vice versa. And comfort is on a scale from -4, which is very uncomfortable, to 4, which is very comfortable. So that one, you just want to be as high as possible. And typically the metric of 0 is used as like minimum time to comfort. And as we can see here, the comfort, as the sensation goes down, the comfort goes up. And then at some certain point where the person is finally equilibrated with their environment, as the sensation continues to go down, the comfort then begins to go down, where it's just too much air conditioning. So this is probably a base case where you start with, you can see the person does not reach neutral comfort. So you might want to optimize this system further, but this gives a good idea of how this design performs. The next study is a warm-up case with cabin comfort, and optimizing the energy usage with TAITherm CAE process automation allows you to get a good idea of exactly what, how much energy you need to provide to different heat up components and how good that's going to do in terms of bringing the passenger to comfort. So we did 3 cases considering variable power to the heat sources, and we used an optimizer to determine the optimal heat that's applied to those different heat sources to get the person to neutral comfort or just comfortable in 5 minutes, I think. So the first one was HVAC only, where we have heat coming from the foot heaters. The next one was HVAC only. I think it was panel and foot heaters. And then the next one was HVAC plus localized heating, which are some new things, and some of them are older things that people are using in cabins. We have radiant panels, we have a seat heater, and we have a steering wheel heater. So a lot of people who live in cold environments already have a seat heater. Steering wheel heater is an option that's already being offered, and these are things that are more comfortable in conventional vehicles as well as EVs. However, they're more significant in EVs because of the energy budget. Then we also have radiant panels, which are kind of new, and people are looking into it. I don't know if anybody offers them yet, but I think they'll be important for electric vehicles. And these kind of things are particularly effective at maintaining comfort because they have the ability to heat the extremities more than the core, and that increases blood flow and increases comfort that way. We use an optimization process in ThermoAnalytics to determine the heat sources. The inputs are the variables with bound conditions. We have a cost function, optimization method, and stopping criteria. The optimization term determines the best values for the variables, and the output is the optimized variables that minimizes the cost function. Here we have animations of the 3 different cases. And in this case, the person is just as comfortable after 5 minutes in all 3 cases. So we're evaluating how much energy is required to satisfy the requirements of the vehicle. And some of the things you can see here is when it's floor mode only, the feet get a little too hot. And if you look at the surface temperatures of the different cases, the surface temperatures are lower for the case where we have the additional heating components, and that tells you that you're expending less energy warming up the cabin and to keep the person hot, as opposed to just directly going from an energy source to the person. And this is an energy comparison of the different components after the optimal condition has been reached. When HVAC is directed at the upper body, it's about 3.4 kilowatts. When it's upper body and legs, it's about 3.3 kilowatts. And then when we have the HVAC on a lower setting, plus the heating panels, including seat, overhead panel, feet panel, and steering wheel, the total is less than 1 kilowatt. So we've reduced the amount of energy that's consumed here by over a factor of 3. And so when all that's coming from the battery, consider that the battery in this case might spend 50% of its power on cabin heating, particularly during the heat up case, not necessarily the entire period of driving. That's a very significant increase in range of the vehicle. The next case study shows battery thermal management. And in this case, we have a pack with a modular design. So you can see there are cells. I'm showing cells here with different components shown in 3 of those compartments, but they're actually in all of them except one, which is where the battery management system resides. And there are 256 cells in total. They're connected 2 in parallel and 128 in series. There are fluid streams representing flow in the cold plate, and the model uses an improved convergence battery model that we've developed recently. For fluid streams, they're set up in a network to distribute flow evenly across the pack, and the channel locations are not optimized for pack cooling. So again, this is like the starting case of where you would go with your vehicle and then optimize your design from here. Fluid stream temperature difference is about 3 degrees Celsius, and you can see how it's distributed here. The inlet distributes flow around the outside of the pack, and then all the channels kind of converge into the center, and that's the outlet in the center. And when we look at the cell temperature distributions, the temperatures of the cells are based on a heat rate that is temperature dependent, and that's individual for each cell here. This is an equivalent circuit model. So the heating in each cell depends on the temperature of that cell. And the temperature difference across the cells in total is about 10 degrees Celsius, which is a lot higher than you want it to be. So this is not an optimal case here. And it actually depends on not just where the liquid is flowing underneath it, but also where the cooling plate in general doesn't have heat sources, which is what's creating that cold spot on the upper right. And if you include heat generation from the full battery management system, that might be a lesser of a difference. But overall, this is a design that would need to be improved to be implemented in a vehicle. And the temperature difference within a cell is 3 degrees Celsius. With this cold plate design, it's hard to get rid of that temperature difference, but generally people want to keep their cells within about 1 degree Celsius. So you can add heat spreaders or alternative cooling or something, tab cooling. There are different ways to reduce that, but this is a good way to predict what that gradient is going to be. Next, we have a Joule heating example. And Joule heating is also known as resistive or ohmic heating, and it's heat that's produced when electric current is passed through an electrical conductor. And this is widely applicable to xEVs. It happens in the battery cell tabs, the electrodes in the battery, bus bars, wiring harnesses, fast charger connections, and wiring, which are actually cooled in the cable itself in some cases. Electronic circuits such as inverters, which must be cooled as well. Positive temperature coefficients heating and HVAC systems, which is an EV component that warms up the air while the heat pump is warming up. And then catalyst heater for exhaust. That's a new requirement for smaller engine vehicles because the catalyst doesn't heat up as fast. And as we're making more hybrid vehicles, the engines are getting smaller, which means the catalyst doesn't heat up as fast, and that means more emissions. So people are heating up the catalyst with resistive heating to minimize exhaust emissions. Then we also have heated seats, steering wheels, and radiant panels. And this is a temperature-dependent heat rate. So the resistivity is a function of temperature coefficient and the temperature difference between the actual temperature and a base temperature. Resistance is a function of resistivity, and then heat is a function of current and resistance, or voltage and resistance. Either one can be used to calculate the ohmic heating. As an example of electric vehicle wiring harnesses, for electric vehicles, there's over 150 pounds or about 70 kilograms of wiring in a single vehicle. And this includes connectors, and I don't know if the weight does, but to consider the temperature and the durability of the wiring system, you also have to consider connectors. For the wires, there are two main categories of automotive wire. PVC insulated are rated to about 80 to 105 degrees Celsius. Cross-linked insulated are rated to about 125 degrees Celsius. And the wires must be protected from surrounding heat sources and undergo self-heating as well due to the resistance of the wires. Typically, the wires are optimized to maintain the temperature of the wires low enough, and also the connectors and things are sized to the right size. So it's important to be able to simulate that. If you have wires and bus bars of different changing shape or cross section, it's important to know how that kind of breaks down from the battery level, which is very big cables, to a lower level such as auxiliaries, which has much smaller cables. Sometimes you need like a holistic approach to be able to evaluate where the current is going and how hot things are going to be, and also protect it from surrounding heat sources. This is an example of a resistive heating model that we made in TAITherm. Here we have temperature, so you can see the temperature depends on the radiation and the surrounding environment. In this case, this is a resistive heating element, which is made of nichrome, a common element used to heat things up, common material. You can also see that it's not exactly an optimal design because the corners have some additional material there, which is something that I wanted to show in terms of current distribution, that we get lower temperatures out there because of the lower current in those extremities. This is the voltage, and you can view this in TAITherm that the voltage basically linearly decreases because it's fairly uniform cross-sectional area. And then we have the current here, and this is where we see the current concentrations on the inside of the bends, and lower current on those sharp corners, which are something you want to avoid. But mainly we chose this design just to have a proof of concept to show that we can model 3D current distribution, which becomes increasingly important when you have bus bars on batteries and connectors with changing cross section and heat concentrations where there might be corners or smaller cross sectional area regions, which are kind of a necessity when you're building something, and really affect how the temperature is distributed there. The next thing we have here is an electric motor example. And there are two components in the motor that are very temperature sensitive. One is the insulating material around the stator windings and sometimes the rotor windings if it's an AC inductance machine. The other one is the magnets, which can get demagnetized. And then you also have things like magnetic saturation when things get too hot, and that derates the power coming from the motor. And these can also be safety issues, but mainly performance and lifetime as well. The insulating material can have a limit between 90 and 240 degrees Celsius, and then the magnets are between 150 and 180 degrees Celsius. And you can see here in this plot that we're plotting the average expected life hours versus the winding temperature. And we have different classes here that are made of different materials, typically insulation materials. But what you see is that you can run an engine hotter, and as long as it's within safety limits, it's not a hazard to the user, but it degrades the longevity of the motor significantly. So we have a durability issue that has to be addressed with thermal management. And to give you an idea of how this is affecting vehicle design, continuous power is typically limited to about 50% of the peak power that a motor can can output due to thermal limits. So already we've got derating by about 1/2 because of the temperature limits of the motor. In this example, we're using an electromagnetic model to calculate the inputs for TAITherm. So TAITherm's the thermal model. This program is the electromagnetic model. And what we get from the electromagnetic model is loss maps for the motor. So we're looking at how much heat is generated in each component. And then we also get a drive cycle from this software that considers motor speed and torque, and then also like vehicle considerations like air resistance and losses in the vehicle. From that, we get loss maps for the different heat sources in the motor. And so we have winding copper loss, iron loss in the stator, iron loss in the rotor, and then magnet loss. They're quite a bit different magnitude for the different losses, but it's important to consider everything that affects that temperature in the motor. Magnet loss is a lot smaller than the other ones, so that could probably be neglected, but we've included it here. These maps get interpolated in TAITherm over a drive cycle. So at each time step, we're just taking this 2D map, interpolating it for the torque and motor speed, and then using that value to apply that heat directly to the components in TAITherm. We also take into consideration the temperature dependence of these loads. So here I've plotted the total loss, which is the sum of the four that we looked at on the last slide. And these are at different temperatures. And you can see they're very different scales, and there's also distributions in here. At a low temperature, the losses are go up to about 500 or 5,500 watts, and at high temperatures that goes well above 7,000 watts. So we have this data generated at different temperatures, and then TAITherm also interpolates between the temperatures to have a temperature dependent performance. This is the drive cycle we used. Vehicle speed is shown on the upper left, which is kilometers per hour. This is the US 06 drive cycle, so a standard drive cycle that's repeated 5 times here. And then the inputs to TAITherm are the motor speed, which is the upper right, and the shaft torque, which is lower left. And then TAITherm is used to calculate the losses, which in this case, I've plotted the total losses on the lower right, and you can see how they depend on the drive cycle in time. The thermal model is an electric motor that is just an example proof of concept at this point, but it has all the components that we need. This one is about 1.5 feet or a half meter in length. And this was scaled up from a smaller geometry. It's got about 7,000 elements in it. So it's really a proof of concept. It's not the most realistic thing because it was scaled up from a different kind of motor. But this shows that we have the capability to model motors, and it's something that we can present to people. These are the heat rates that are interpolated from those maps in TAITherm. This is a direct output from TAITherm. So we have the stator windings that go up to about 2,500 watts. Stator core goes up to about 1,000 watts. Rotor core about 60 watts, and then the magnets are less than a watt. Then we have temperatures, and you can see between these components there are a lot of different heat paths. There's contact resistances between components, and some components are like the windings are in an epoxy resin, and those fill in the stator slots. So there can be some contact resistance there, but they're bonded together. And then we have the thermal conductivity of those resins and how the stator is connected to the housing. We also have heat transfer coefficients in the motor, which are dependent on RPM and temperature, possibly. I think in this case it's just RPM that it's dependent on. And so that is included in this model. We've used correlations from literature that are a function of motor speed. And now I'll talk a little bit about advancements in system level integration with 3D thermal modeling. And we have some new tools to do this. In TAITherm, we've recently integrated an Excel interface, which allows you to import and export data to and from Excel. And it also allows you to access subsets of table variables in TAITherm, which I don't think they're called table variables, but they're 2D variables. And you can use symbols to access the value, size, and indexing into those array data. And then you can write back to Excel using a variable assignment task. We also have MATLAB integration now, which is included in TAITherm 2020.2 and newer. MATLAB is supported from 2018B up through 2020B. And the latest versions of MATLAB are included in each release of TAITherm. So twice a year, those get updated to the latest versions of MATLAB. And this uses the MATLAB C++ API, so it's a direct link to MATLAB. This is the workflow. We have TAITherm integrations of different applications in TAITherm on the lower right, or in TAITherm on the lower right. That could include TAITherm, CFD, Python, MATLAB. Well, MATLAB is the upper portion, but the MATLAB code gets written from a defined text file, which takes TAITherm variables as input. It runs MATLAB, which executes the functions and then saves the variables in the workspace. And then TAITherm will read the variables directly out of the workspace into TAITherm, and those are then used in the other applications in TAITherm. So it's a round trip thing where we're importing data to MATLAB directly in the scripts that it runs, and then reading the workspace data into TAITherm. This is an example that we did with MATLAB Simulink and TAITherm, and this is an HVAC cool down scenario. So Simulink runs a thermostat model, which predicts the HVAC heat rate. That goes into the TAITherm model, which is run with transient thermal boundary conditions with a weather file with solar loading, sun's changing throughout the day in position. And then it's sitting on a hot asphalt surface, which radiates heat into the vehicle cabin from underneath. And the temperature of that asphalt depends on the ambient weather conditions. That can be quite significant. So TAITherm offers a very powerful tool to predict cabin modeling. But you do have to know the boundary conditions in the cabin of the HVAC system. And that can be kind of hard to tell without some scripting or 1D modeling. So we have the MATLAB thermostat model, which takes the cabin air temperature from TAITherm and predicts the HVAC heat rate. And these are the results from that. We have the heat rate, which basically just goes between two values. And then the temperature versus time is maintained between 16 and 24 degrees Celsius. So it's a fairly simple case, but a proof of concept. And in this case, the cabin air temperature is the variable that's used in this algorithm, but you could also use person comfort or surface temperatures or something like that. So it's an interesting concept. If you were to feed the comfort level of the person back into the 1D model, you could get a much better prediction of how you need to regulate the cabin air temperature. So there are different ideas that you could use to make this a very valuable thermostat simulation, and possibly determine what kind of control scenario you want in the vehicle, and what kind of feedback you have in an onboard algorithm to regulate the AC unit. Another example here is the electronetwork thermal electric coupling with TAITherm. In this case, we have an alternator, which is a type of electric motor that's just ran in reverse as a generator. And then in TAITherm, we have a 3D thermal model. So the alternator predicts the heat rate and the heat transfer coefficient in the alternator as a MATLAB Simulink model, as well as other MATLAB algorithms and scripts. So it's combined. Those are mapped into TAITherm. TAITherm predicts the alternator temperature and wire temperature, and those are used in Simulink to predict the performance of the alternator. And the main thing we were looking at here was the decrease in alternator output from magnetic saturation when the temperatures get too high. But those are also relatively significant considerations in electric motors. But the point is here that we needed temperature in the electrical design of the machine to predict how much the battery is going to be charged, and that determines what kind of control scenario you can use for the electro network system in order to maximize fuel efficiency and minimize battery degradation and low state of charge. We also have some photovoltaic solar panel modeling capabilities in TAITherm, and vehicle integrated solar panels extend the range of EVs and power auxiliary components as well. These are some examples of vehicles that are using solar panels. You could put them all over the vehicle, but typically they're going to be on the roof and maybe the hood and back of the car, but typically on the roof. We now have translucent solar panels, so it's basically a skylight that produces electricity. They can also be structural. People are using polycarbonate to manufacture this type of roof, and it's not only structural, you can see through it, it generates electricity. So as an example, the 2020 Hyundai Sonata Hybrid goes an additional 2 miles per day. The Sono Motors vehicle expected in 2022 can go up to 34 kilometers a day additional due to these solar panels. That one has solar panels all over it. So this is an example of the thermoelectric photovoltaic model in TAITherm. And this is showing the importance of predicting the temperature dependence of that PV output. So this is using a weather file which predicts the solar loading throughout the day and position of the sun. And we have two cases here. One is considering the temperature dependence in TAITherm and one is not. And you can see in these plots here, there's quite a bit of difference there. So in conclusion, thermal management and vehicle components is becoming increasingly important as companies electrify their vehicle fleets. HVAC design really influences the range of xEVs, and human comfort prediction is a critical aspect of engineering to consider to meet energy budgets. The new strategies for different components in electric vehicles have been demonstrated using TAITherm and how that affects your design. And then 3D thermal system integration with 1D modeling can allow full vehicle modeling, which takes into consideration solar loading and boundary conditions that are changing throughout the day. So you can get an idea of how that influences all your different components. And TAI is undertaking a major initiative right now to meet customer requirements as xEV manufacturing is taking off. And that's all I have today for the presentation. So I think we'll take questions now.
Yeah, thanks, Zach. We had some come through. I have a couple more coming through right now also. So let's start with, can we model battery lifetime and thermal runaway?
Yes, we have tools that both models come from the National Renewable Energy Laboratory, and we've licensed them in TAITherm. They come with the battery extension for thermal runaway and with Cotherm for the lifetime model. So the lifetime model's in Cotherm, and it runs with TAITherm simultaneously and predicts the resistance increase and capacity fade of the battery. And then the thermal runaway model is directly in TAITherm, and that predicts the exothermic reactions inside the battery when that occurs, and that gives you the heat rates that are applied to the 3D geometry. And people are looking at mitigating the propagation of thermal runaway from cell to cell, or at least slowing it down. I think the criteria now is 5 minutes for a person to get out of a car. So they're looking at how to optimize their design to they're kind of trade-offs, the lifetime and the safety aspect, because you have to add components for safety that could actually increase temperatures during runtime. So it's important to consider them both and make sure that your passenger is going to be safe and satisfied with vehicle design.
Okay. What other programming languages are available for scripting in TAITherm, and what options are available for other languages like MATLAB?
Okay. TAITherm supports JavaScript and Python directly in the scripting editor, and that's native to TAITherm. For something like MATLAB, we have Cotherm for MATLAB coupling, which has those built-in interfaces. It's very easy to use. MATLAB can also be run from TAITherm if you have something that requires that kind of functionality, and that could be run from a script using the Python MATLAB API. So that's possible. Also, Python has a lot of libraries that come from MATLAB functionality. So chances are, if you've written something in MATLAB, you could easily port it over using the same kind of library functionality and run that directly with Python in TAITherm.
Okay. Can the ohmic heating model handle electric contact resistance?
Well, it's not something that we've built in right now, but the inputs are definitely available there. We have the current in the wires. You can have the geometry in TAITherm, and the Joule heating model is actually a script right now in TAITherm, which means that you can change it or add to it. So the scripting allows a lot of flexibility in what you can model, and you could easily put in a contact resistance there that uses that current and produce the heating, and then use the TAITherm API to apply that heating to your components in TAITherm. So it's not like a built-in feature, but we have the capability to add that, and it probably wouldn't be a lot of effort.
Okay. One side is a 0D model when it comes to two-way coupling. Why does TAITherm insist on 3D geometry?
3D geometry allows you to get more accurate temperature predictions. In total, when you've got larger models that require like outdoor solar loading conditions and things like that, but also it allows you to set boundary conditions based on what you know them to be or can predict from a CFD software. So in a 0D or a 1D tool, you might have some kind of effective resistance between two components in a model that might represent convection or conduction, or some combination of convection, conduction, and radiation. Whereas in TAITherm, you specify a heat transfer coefficient on that component, which is a lot easier to predict. You have 3D radiation, multi-bounce radiation between components and between like the sun and the ground and the vehicle. And in that case, you would specify a surface condition. Then you also have conduction, which is specified just with the material properties and cross sections in your geometry. So those are things that can be found using correlations that are readily available. They can be predicted with a CFD simulation, or might just come out of knowing things like heat transfer coefficients and surface conditions. So TAITherm is calculating heat transfer between different components, but basically it's easier to set up the boundary conditions in a way that you know what they are, and that way you're not required to predict some kind of equivalent resistance from between two components that is actually a combination of different effects, and requires some kind of calibration or physics modeling to be able to determine those components values.
All right, and same person, is the heat transfer characteristic here?
Yeah, I mean, TAITherm is a heat transfer modeling software. So I guess if you're asking if it's characteristic of actual behavior, I mean, the model is as realistic as you make it. So if you don't have a lot of information about the values in your model, it can tell you the behavior of how things are going to heat up and what the interdependencies are, and maybe a principal component analysis determining what things you have to change. But without real accurate inputs, the outputs aren't going to be really accurate. If you do testing and tear down analyses and things like that and get very accurate inputs to TAITherm, the outputs are going to be very accurate. So it's really a question of what you need to do to get the kind of results that you require, and that determines how characteristic the simulation is.
Thank you, Zach. That will complete today's webinar. We appreciate everyone for attending. You'll receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thank you, everyone, and have a nice day.